Hello, and welcome back to Physics 141 Classical Electromagnetism 1. So far, we have discussed about the polarizability of an atom or a molecule, which just determines how much or how easily a material can be polarized. So alpha is the polarizability, and it's proportional to the induced dipole moment. The dipole moment induced by an external field E. So we also have discussed about polarization, which is basically just the dipole moment per unit volume. So since the polarization is just proportional to the dipole moment, and the dipole moment is proportional to the electric field, then the electric field must be proportional to the polarization must be proportional to the electric field. So we also have discussed about the electric displacement of a dielectric material, and it's basically just the total electric field of your material. Electric field plus the polarization field, for instance. So for this lesson, we will try to relate the polarization and the electric field of a polarized object. And if you'll notice, there is a direct proportionality between these two quantities. So for this lesson, we will only focus on linear dielectrics. So materials wherein the polarization varies directly with the electric field. So the relationship between the linear relationship between the polarization and the electric field inside a polarized object is given by this equation. So epsilon naught is the permittivity of free space, and this Greek variable here, C sub E, what we call the electric susceptibility. So it's pretty much related to polarizability. So if your material is susceptible to electric field, then it can be easily polarized, and vice versa. So the electric field here that we are considering is now the total field. It's due to the external field plus the internal field, or it could also be due to the free charges plus the electric field to the bound charges. So this is already the total electric field inside your dielectric. So we can also write now the direct relationship of the displacement and the total electric field. So since we can now write the polarization P in this manner, so doing that will give us this relationship. The electric displacement basically just your total electric field of your dielectric. The proportionality constant is just the permittivity of free space. So this is given by 1 plus the susceptibility times the permittivity of free space. So you may have encountered actually about permittivity before, or rather the relative permittivity, the ratio of the permittivity of the material times over the permittivity in vacuum, and that is actually what we call the relative permittivity, or as you call it in your university physics or general physics, the dielectric constant of the material. So the book actually uses a different notation for relative permittivity, but we will just the notation capital K, because we have been using this notation starting with your university physics or in general physics or physics 41. So if you are given the dielectric constant, you can solve for the permittivity by just multiplying epsilon naught, and you can also solve for the electric susceptibility. So the electric susceptibility from this equation is just K minus 1. So from this relationship, we can actually derive that the electric field inside the polarized object is essentially the electric field in vacuum, or the electric field when there's no dielectric, divided by the dielectric constant. So actually you have derived, or you have encountered this expression before when you discuss about capacitors with dielectric. So the electric field inside the capacitor with dielectric will actually decrease by a factor of 1 over K. That one. So this is the electric field in vacuum, the original electric field. And when you insert a dielectric with constant K, the new electric field becomes 1 over K times the original electric field. Okay. So let's now go directly to examples. So here we have a conducting sphere, meaning it's a conductor, it's a total charge Q, and then you coat it with a dielectric. So since this conducting sphere is charged, then therefore it has an electric field, and that electric field will polarize the dielectric here. So the dielectric is now polarized because of the electric field of this, and there will now be an electric field within your dielectric, polarized dielectric. So you are asked to locate all of the bound charges and find the electric potential at the center relative to infinity. So let's first start with the first problem. So we are asked to locate all of the bound charges. So if you will notice, for the bound charges, you need the polarization P, because the bound charges depends on P, the polarization. But we cannot solve for the polarization if we don't know the electric field. So we still need to find the electric field also. And since we are dealing with dielectrics here, we need first, it's easier actually to get the electric displacement first. So what we will do here is we will find the electric displacement first, then find the electric field, then find the polarization, and find the bound charges. Okay, let's start with the Gauss law for dielectrics. So we will just use the integral form. So the closed integral of d dot dA equal to the free charges UF. So in this case, the displacement, due to symmetry, the displacement will actually be uniform at all for points with the same distance r from the center of the sphere. So this will just reduce to d times the area, which is area of our Gaussian surface, 4 pi r squared. So we'll just make a Gaussian surface now, a spherical Gaussian surface. And in this case, the free charges are only from the conductor. Take note, there are no free charges within the dielectric. It's all bound charges. Charges are not free to move within a dielectric. The free charges is only Q. So from here, we see that the displacement is just Q over 4 pi r squared. So this is actually the displacement from R greater than A. So inside the dielectric and outside the dielectric. There's no displacement inside your conducting sphere because this is a conductor, not a dielectric. The displacement only applies to dielectrics. So in this case, your electric field, your electric field in this case, electric field, due to assuming Q is positive, the electric field will actually be radially outward. What will happen is there will be negative bound charges on the inner surface of the dielectric, and there will be positive bound charges on the outer surface of the dielectric. And these bound charges will create an internal field in the opposite direction. But still, the electric field due to the conducting sphere is stronger, so the electric field in the dielectric region will still be radially outward. So the electric field due to the bound charges is not sufficient to reverse the direction of the electric field. So hence, the direction of the displacement is also in this direction. It's also radially outward. Take note from our earlier result, the electric displacement is basically just the total electric field. So they have the same direction. Okay, so from here, our D vector, displacement vector, has a direction of r hat. So knowing the direction, knowing the displacement vector, and using this, we can now solve for the electric field in the polarized region, and actually even outside the polarized region. So just divide D by epsilon. So in this case, I forgot to mention the given permittivity of our material, our dielectric, as epsilon. So just divide this by epsilon. So you will have Q over 4 pi epsilon r squared r hat. So this is the generic form of our electric field in the dielectric region. So actually, outside the dielectric region, in this region here, the electric field will actually still look like this. But since this is now vacuum, then the permittivity is equal to epsilon sub 0 or epsilon naught, the permittivity of free space. Okay. So we now have D, we now have solved E, we can now solve for the polarization. So it's just epsilon naught susceptibility times the electric field. So just multiply this by epsilon naught and then susceptibility. So you will get an epsilon naught over epsilon, which is just the inverse of your K, your dielectric constant, essentially. But since we are not given the dielectric constant, we are given the permittivity, then we will not convert that ratio. We will have epsilon naught C susceptibility Q over 4 pi epsilon r squared. So if instead you are given with the dielectric constant K, then you can convert this factor epsilon naught over epsilon as 1 over K r hat. So this is the polarization now. The bound charges is the negative divergence of this polarization, and it will actually give you a 0. So even though from the looks of our polarization vectors it's diverging, but there's a special case here as what we have obtained in the previous chapter. Your polarization is inversely proportional or proportional to 1 over r squared, then it has no divergence. So if P is 1 over r squared, such as in this case, our P is proportional to 1 over r squared. So that will have a 0 divergence, and therefore 0 volume bound charges. So no volume bound charges for this case, only surface bound charges. Negative surface bound, negative charges, charge density in the inner surface, positive charge density in the outer surface. So for the bound charges, we use the formula P dot n hat. So n hat, so this is your dielectric. It will actually have two surfaces. So for the inner surface, this is the direction of n hat, actually negative r hat. And for this surface here, the direction of n hat is radially outward, so that's actually r hat. So you just dot this with your n hat, depending on which surface you are referring to. For instance, in the inner surface, n hat is negative r hat. So you have r hat, that negative r hat, you will get a negative value, hence the negative charges here. So your bound charge densities will be negative epsilon naught just for r is equal to a, and positive value of this epsilon naught x EQ over 4 pi epsilon B squared for R is equal to B. So those are the location of your bound charges and their amount of your surface bound charge density. So let's now go to the second problem. Find the electric potential at the center of this configuration, so at R is equal to 0, relative to infinity. So for this case, we are trying to find the potential at R is equal to 0. So basically, using the E.dl formula, from our reference point is infinity, and we are trying to find the potential at R is equal to 0. So we can actually divide this into 3 regions. We have from infinity to B, outside. And then from B to A, within the dielectric. And from A to 0, inside the conductor. But the electric field inside the conductor is 0. So this will have no contribution. And then we already have solved for the electric field within the dielectric. Actually just equal to Q over 4 pi epsilon R squared R hat. And similarly, outside, it's just the same but with a different permittivity, 4 pi epsilon naught R squared R hat. So our DLs here are just dr R hat. So substituting these results, you will have inside the integral, you will have dr over R squared. So that's just a very easy integral. You do that and you will get the potential at the center of the sphere as Q over 4 pi 1 over epsilon naught B plus 1 over epsilon A minus 1 over epsilon B. Okay. So in summary, these are the location and amount of bound charges, negative charges in the inner surface at R is equal to A, and on the outer surface, R is equal to B, positive charges. And for letter B, the potential at the center is given by this equation. For our next example, we have a capacitor with dielectric. So what happens to the capacitance of a parallel plate capacitor if you insert a dielectric between its plates? So you actually have solved this problem before. So this is the classic problem in capacitance with dielectrics. So for a capacitor without dielectric, its capacitance is actually epsilon naught A over D. It only depends on area of its plates and the distance between its plates. So in this scenario, the upper plate is usually positively charged, positive sigma, and the lower plate is negative sigma. And this will cause to have bound charges and the upper and lower surface of your dielectric. So there will be negative bound charges here, so sigma B, and there will be also positive bound charges here, sigma B. And this sigma is negative, this sigma is positive. So you will notice that there will actually be an electric field upwards due to the bound charges. But this electric field is far weaker as compared to the original electric field without the dielectric. EB. such that the net electric field inside the dielectric or inside your capacitor is still in this direction. It's still downwards. So the net electric field E is still downwards because the electric field due to the bound charges is much weaker as compared to the original electric field. The electric field without or the electric field due to the free charges, positive sigma and negative sigma at the upper plates and the lower plates. Okay, so this electric field is actually now 1 over k times d. It's actually smaller by a factor of 1 over k as compared to the original electric field. So if we try to calculate the potential, the new potential now, the new potential in between the plates will now be the new electric field times the distance. So the new electric field is just the original electric field without the dielectric over K. Now, this electric field here, E naught, this is actually just the field between two sheets of charges of opposite sign, and it's equal to sigma over 2 epsilon naught. It's related to the charge density, sigma. So this is actually basically just sigma d over sigma over epsilon naught. There's no two factor. Sigma over epsilon naught. Sigma over epsilon naught k. So if we now try to solve for the capacitance of this capacitor, if its total charge is q, sigma can actually be written as the charge per unit area. So this becomes epsilon naught a times k epsilon naught a. So if we now try to find the capacitance as charge per unit voltage, so you now have q over qd over k epsilon naught a. And you will get k epsilon naught a over d, or since epsilon naught a over d is just the original capacitance, it's just k times the original capacitance. So you actually have obtained this result. The purpose of the dielectric in a capacitor is to increase the capacitance. So the dielectric constant actually serves as the multiplying factor for the capacitance. So if you have a dielectric constant of 5, your capacitance, your new capacitance becomes 5 times the original capacitance. So that's all. So in summary, the dielectric constant or the dielectric serves as the multiplying factor. Okay, third example, still a capacitor with dielectric. But in this case, we now have two dielectrics in between the plates of our capacitor. So we are asked to find the displacement, the electric field, the net electric field, and the polarization in each of the slab. The potential difference between A and B, so between the plates of the capacitor. We are also asked to locate and find the amount of all bound charges. And using the result in C, we recalculate the electric field in each slab using the result that we will obtain in C. Okay, let's first start with the first problem. Okay, so in this problem here, we will have, since the upper plate will be positively charged, there will be a positive sheet of charge here, then there will be a negative bound charge on the upper surface of slab number 1 or dielectric number 1, and there will be positive charges at the lower surface of slab number 1 or dielectric number 1. So since the lower plate is negatively charged, then there will be positive bound charges at the lower surface of slab number 2, and there will be negative bound charges at the upper surface of dielectric number 2. Take note that the magnitude of these bound charges for every slab are actually the same. They only differ in the sign. Basically, our slabs are initially neutral, so they should have a total charge of 0. Okay, I forgot to mention that our K1 here, the first dielectric, has a constant of 2, and K2 1.5 or 3 halves. Okay. I forgot to place the given. Okay. So find the displacement. So what we will do, we'll use Gauss law for dielectrics. So we will make a Gaussian surface here. It could be a box, or sometimes it's called a Gaussian pillbox. So we make a Gaussian surface, a box, a Gaussian surface. So, by the way, let's first find the directions of D, E, and P first. So, take note that without the dielectric, the direction of the electric field is downwards. So, meaning the net electric field in each of the slabs will still be downwards. So, the direction, for instance, of E1 in this case, still downwards. And the electric field in the slab number 2 is also still downwards. That's the total electric field, the original minus the electric field of the bound charge, or plus the electric field of the bound charges. So this means that if the electric field, total electric field is downward, then the total displacement is also downward. So D1 will still be downwards, D2 will also be downwards. And since the negative charges are on the upper side, the positive charges on the lower side, the dipole moment will be directed from the negative to the positive. And hence, the polarization will also be in that direction. So this will also be the direction of our polarization, P1. And same for P2. So all of these three, the displacement, the electric field, and the polarization are all directed downwards. So that we can have a reference for our direction, we will set the vertical axis as our z-axis. This will be our z-axis. So the lower plate location we will set it as our z is equal to 0. In between, this is z is equal to d, because this distance is d. And the location of the upper plate is d is equal to 2d, because this is d, this is also d, so that length must be 2d. Okay. So I'm just gonna solve for the electric field, displacement, and polarization for slab number 1. You repeat the process and you solve those values for slab number 2. So this is our Gaussian surface now. If you will notice that there's no displacement we are using a cube here. Now, a cube has 6 sides, and only one side will contribute, or one surface will contribute, this lower surface here, where the displacement is D1. In the upper surface of the cube, there's no dielectric there, it's a conductor, so there's no electric displacement. And at the sides of the cube, there will also be no contribution, because our Gauss law for dielectric states that the dot product between the electric displacement and the area. So in that case, the d dot dA, since the area vector is always perpendicular to the surface, so this is the area vector. These are the area vectors. So it's down here, this side here, it's perpendicular to the surface. So if you dot d1 dot dA, you will get 0, because the angle between them is 90 degrees. So only one surface will contribute. this surface here, d1 dot this area here, area enclosed in the lower area. So you will have, say, d1, this is free charges. So you will have just d1 times the area enclosed, lower area of the box. The free charges will just be due to the enclosed surface charges. The free charges are the ones in the upper plate, in the metal plate, so sigma. So to get the enclosed free charges, it's just sigma times the area enclosed. So divide both sides by area enclosed, you will get d1 is equal to sigma. And in terms of vector, it's the direction is actually negative z hat, since it's downward. Okay, so knowing d1, I can now solve for e1. So you just divide the displacement by the permittivity. But we are not given with the permittivity. Instead, we are given with the dielectric constant, which is 2. So to solve for the permittivity, it's just the dielectric constant times the permittivity of free space. In this case, for K1 equal to 2. So divide this by essentially by the permittivity E1. So it's just D1 over E1. For E1 is just K times epsilon naught. K1 times epsilon naught, or 2 epsilon naught. So it's essentially sigma over 2 epsilon naught, negative z hat. So given E1, we can now solve for P1, the polarization. It's just epsilon naught, the susceptibility times the electric field. This is the susceptibility of 1. So to solve for the susceptibility of slab number 1, K1, so take note K is just 1 plus the susceptibility. So meaning the susceptibility is K minus 1. So K1 minus 1. So 2 minus 1, you get 1. So essentially this is just 1. You will get sigma over 2 negative z hat. So these are the displacement, electric field, and polarization vectors in slab number 1. You repeat the process for slab number 2. You make a Gaussian surface in this region here. And then solve for D2, E2, and P2. Okay. So you will actually get these values. So you will actually get these values for D1, E1, P1, D2, E2, and P2. Okay. For the second problem, we are asked to find the potential between the plates of our capacitor VAB. So how do we do that? So we use the E dot dl formula. So negative E dot dl from B to A. So of course, from B to A or from A to B, it's actually 2 regions, from 0 to D, from D to 2D. So we can actually use that. So from 0 to D, the electric field there from 0 to D is E2. And then from D to 2D, from D to 2D, the electric field there is E1. So we already have the electric fields, the DL here. The DL vector is just dz, z hat. So you use that, the value of the electric field, and you will just be left with the integral of dz, because the electric fields E1 and E2 doesn't depend on z. And you will get VAB is equal to 7 sigma d over 6 epsilon naught. Okay. For the third problem, we are asked to find the amount of all bound charges and locate the bound charges. So since we already know the polarization, so in this case, there will be no volume bound charges in slab number 1 and slab number 2 since our polarization is constant. So it has no derivative, so it has no divergence. So there are no volume bound charges, only surface bound charges. So there will be negative here, there will be positive here, there will be negative again here, and there will be positive here. So to solve for the bound charges, sigma b, you just dot the polarization dot with n hat. Okay, so you must consider this very carefully, the direction of n hat. For example, for slab number 1 or dielectric number 1, it will have two surfaces, the upper and the lower surface. For the upper surface, this is the direction of n1 hat. For the lower surface, this is the direction of n1 hat. For the lower dielectric or the second dielectric, it will have two surfaces. So this will be the n2 hat for the upper surface, and this will be the n2 hat for the lower surface. So take note that the area vector, the n hat or the normal unit vector, always perpendicular to the surface and out of the surface. Take note that out of the surface. So this is our surfaces here, out of the surface, out of the surface. So for instance, for in this case, n1 is this is the z hat direction. So all of the upward direction is z hat. All of the downward direction is negative z hat. Negative z hat. So for instance, I will just solve for the first dielectric. For the first dielectric, for the upper side, it's actually P dot, the upper side is z hat, so P dot z hat. For the lower side, it's P dot negative z hat, for the lower side, for the first dielectric. So this is for actually at the location of z is equal to 2d, and this is the location of z is equal to d. So essentially, you just you already have solved the polarization. It's actually just this is equal to, this is P1, sorry. P1 is sigma over 2 negative z hat. So P1 over, our P1 is sigma over 2 negative z hat. So you have negative z hat, that z hat you will have negative. So this will actually be equal to negative sigma over 2. And this is negative z hat, that negative z hat, this will actually positive sigma over 2. So in this upper surface here, there will be negative sigma over 2. In the lower surface, there will be sigma over 2 for the first dielectric. You do the same for the second dielectric, and you will find out in the upper surface, there will be negative sigma over 3, and in the lower surface, positive sigma over 3. Okay. So for the last problem, you are asked to use the obtained charge densities in C and recalculate the electric field in each slab. So you will actually use or do again Gauss law. But now you will be using the original form of Gauss law. So there will now be free charges here which are positive, and there will be bound charges here which are negative. So the charge enclosed now will now be due to the bound charges plus the free charges. So in this case, the free charges is just sigma times the area enclosed, and the bound charges will just be in this case sigma b, or since this is the conductor number dielectric 1, sigma b1 A enclosed, or just sigma plus sigma b1 A enclosed. So you do that using the original Gauss law. E dot dA is equal to Q enclosed over epsilon naught So use the original Gauss law to verify that you will still get the same result as you have obtained in letter A. I will leave that as an example, as an exercise for you. So as a summary for this problem, for letter A, these are the displacement, electric field, and polarization at each of the slabs or dielectrics. For letter B, this is the potential difference between our capacitor plates. And for letter C, these are the location and amount of bound charges for both the upper and lower surfaces for the two dielectrics. And using these results in letter C and recalculate again the electric field, you will still get the same results. Okay. This is the last example. Example number 4. So we have an insulated cylindrical capacitor here. So this is a solid conducting cylinder. And then the outer shell is a also a conducting cylindrical shell. So this is a cylindrical capacitor. So there's a charge Q in the solid conducting cylinder, and of course in the conducting cylindrical shell you will expect it to have a charge of negative Q. So the cylindrical shell must have a charge of negative Q because this is a cylindrical parallel plate capacitor. So in between these two, the positive Q and the negative Q charges or conductors, there are two regions. So in the region R is equal to from A to B, in this region from A to B, it's vacuum. And from B to C, R is equal to B to R is equal to C, it's now a dielectric with dielectric constant K. So you are asked to find the electric field everywhere and find the capacitance per unit length of this capacitor. So let's start with the first problem. Okay, so there will be, if you will notice, find the electric field everywhere, there will be 4 regions. Region 1, region 2, region 3, and region 4. Obviously, for region 1, the electric field here, since this is just inside the conductor, then E1 is 0. There's no electric field inside the conductor because charges are only reside at the surface. The positive Q charge only reside at the surface. For region 2, it's non-zero. For region 3, it's non-zero. But for region 4, since the total charge enclosed is positive Q and the negative Q, it's 0. Then in region 4, it is expected that the electric field is also 0. So the only non-zero electric fields are in region 2 and in region 3. Okay, so what will happen now in this scenario? So assuming Q is positive, then there will be negative charges in the inner surface of our dielectric, and there will be positive charges at the outer surface of our dielectric. So this is what happens. So there will be induced charges, bound charges at the inner and outer surface of our dielectric. So we only need to find 2 electric fields, E2 and E3, in region 2 and in region 3. So let's first use Gauss law for dielectrics. So this the dielectric or electric displacement is actually similar. The form of the electric displacement for region 2 and region 3 are actually similar because if you make a Gaussian surface in region 2 and in region 3, they will have the same free charges. The free charges will always be due to the conductor here, the solid conducting cylinder. Take note, free charges are only from conductors. So since region 2 and region 3 have no free charges, the only free charges can only be found in the solid conducting cylinder, then a Gaussian surface in region 2 and region 3 will result in having a free charges enclosed of positive Q or Q. So due to symmetry, again, the electric displacement is uniform at all points with the same distance from the center of the cylinder. So this will just be equal to D times A, where ang A is ang area of the cylindrical Gaussian surface, 2 pi SL. So D will just be equal to Q over 2 pi SL. And the direction of this is S hat, in the same direction as the electric field. So the electric field's actually direction here is radially outward. So this will be the direction of our electric field, E2 and E3. So similarly, the direction of displacement will also be in that direction. Okay. So in region 2, so E2 will just be equal to the displacement, this displacement divided by epsilon naught, since this is vacuum. You will get Q over 2 pi SL, 2 pi epsilon naught SL S hat. And in region 3, since we are given the dielectric constant, so E3 will just be equal to the displacement over the permittivity epsilon. So since we are not given the permittivity, but instead we are given K, so we can actually just use K. So the permittivity is just K times epsilon naught. So we divide D by K epsilon naught, and you will get Q over 2 pi epsilon naught K SL S hat. So these are now the electric field everywhere. In region 2, in region 3, and in region 1 and 4, inside the solid conducting cylinder and outside of the capacitor, they're all 0. Okay. For the second question, our problem, we are asked to find the capacitance per unit length of this capacitor. So the term capacitance per unit length, so since capacitance is just Q over the potential difference, V, in this case, the potential difference between A and C, VAC. Actually, we can start from just B na lang, because we will be measuring from here, from 0. From this point here to this point here, we will find the potential difference basically at these 2 points. So QV over L. So that we can solve this, we need to know the potential V. So the potential V will now be from C to 0 of E dot dl. And from C to 0, it's actually 3 regions. From C to B, from B to A, and from A to 0. C to B. The electric field from C to B is actually E3. And then from B to A, the electric field there is actually E2. We have solved earlier. And from A to 0, the electric field there is E1, which is actually 0 because that's the electric field inside the conductor. It's actually 0. So we only have 2 terms, E3.dl, E2.dl. And the dl is basically just ds s hat. Our E2 and E3 are in terms of s hat, as a functions of s hat. So actually, the result that we have obtained before is 1 over s. It's proportional. E2 and E3 are proportional to 1 over s. So we'll have something like ds over s. And the integral of ds over s is something like an ln. So you will have results in terms of ln. So knowing V, you substitute it here, and you will solve the capacitance per unit length as 2 pi epsilon naught over ln of B over A plus 1 over K ln of C over B. Okay. So to summarize this problem, these are the results. So for letter A, the electric field everywhere is 0 inside the solid conducting cylinder and outside of our capacitor. So for letter B, the capacitance per unit length will actually only depend on the radius and the dielectric constant K. So actually, if there is no dielectric, for instance, so K is just equal to 1, then it just becomes a capacitor in vacuum. Yeah. So this is equal to 1. So this is the capacitance per unit length if you only have vacuum in between the plates of your cylindrical capacitor. Okay. So that's the end of this lesson. So this is the second to the last lesson for this chapter. And for the last lesson of this chapter, we will be discussing about how to solve boundary valued problems but now with uh, dielectrics. So I will see you again in the last lesson for this chapter.